Hi, everyone. Thanks for joining today's Moldflow webinar. My name is Beth, and today with me I have Dan Milligan, who will be presenting for us on utilizing Helius PFA with Moldflow Insight. As usual, throughout the presentation, you'll have the opportunity to ask us questions along the way. We may wait till the end to answer some of these questions, but please be assured that we will do our best to get them all answered for you today during the webinar. This webinar will also be posted to our YouTube channel, and as usual, you will also receive an email with the direct link to the YouTube posting as well as to our Autodesk box folder where the slide deck will be uploaded. And with that, I'll go ahead and pass it over to you, Dan.
Thank you, Beth, and good morning, everyone. Thank you for joining. As Beth mentioned, my name is Dan Milligan, and I know I've met a few of you in person or over the phone, but just as a brief intro, I'm an advanced materials technical specialist here at Autodesk, and so my role is to enable the users of our Moldflow products to utilize the results of those manufacturing simulations in their structural analysis of their plastic and composite parts. And that's the subject of the presentation today, is I'm going to provide an overview of a piece of software that's provided by Autodesk called Helius PFA. And Helius PFA, at a high-level overview, is a tool that allows us to take results from a Moldflow simulation and utilize those results in our structural analysis. And this can be thought of as enabling as-manufactured plastic simulation. What I want to show here is really the workflow for how Helius PFA fits into the workflow for taking Moldflow results and transferring them or mapping them over to our finite element analysis. You can see on the left-hand side, we use Autodesk Moldflow Insight to simulate the filling process, where we can get aspects of the filling process, such as fiber orientations for fiber reinforced plastics, or where weld lines or knit lines may be forming in our part. And then the middle part is where we can use the Helius PFA software to transfer the results of those manufacturing simulations, such as the fiber orientations or the weld surfaces, and utilize those as inputs into the material properties to feed our finite element analysis. And so in addition to fiber orientations and weld lines or weld surfaces, we can also define nonlinear material properties. Now, as plastics engineers, you know this is very important in that when we have high strain levels or high deflections in our plastic parts, the plastic or fiber reinforced plastic materials start to behave very nonlinear. And so being able to account for the nonlinear stress strain behavior in these plastic materials allows us to get the most accurate representation of our plastic part. Now, what we've done with the 2018 release of both Moldflow Insight and Helius PFA is we've actually provided Helius PFA as an entitlement as part of all 2018 Moldflow Insight Ultimate subscriptions. Now, Insight Ultimate maintenance users and other users that are using various levels of Insight, standard or premium, can gain and use Helius PFA, but a separate license is required for those users to utilize Helius PFA. So again, let me just summarize that. Anyone that is subscribed to the 2018 Moldflow Insight Ultimate level gets automatic entitlement to Helius PFA. And if this workflow interests you, any user at any level of Insight and then Insight Ultimate maintenance users can get access to this software as a separate license. Now, I mentioned that Helius PFA really connects Moldflow Insight and finite element analysis. So there are two main finite element analysis packages that Helius PFA is currently integrated with. That includes Abacus, both the most recent releases, 2016 and 2017 versions of Abacus, and also ANSYS Mechanical. 4 releases are now supported with the 2018 release of Helius PFA. We go back to ANSYS 17.0, .1, and .2, and the most recent major release of ANSYS 18.0. Now there is a newer release, minor release of ANSYS Mechanical. I believe we're up to ANSYS 18.2 actually. And one of the unique aspects of when Autodesk made the business transformation from perpetual licenses to subscription licenses is that we're now able to release both our Moldflow and our Helius PFA products on a quarterly release schedule. And what that allows us to do is it allows us to ensure that both Moldflow and Helius PFA are compatible with the most recent versions of the finite element analysis solver that were released in those previous quarters. So what you'll see is with the .1 release of both Moldflow and Helius PFA, the 2018 .1 release, we will upgrade the FEA compatibility to include the most recent versions of the FEA solvers. Now I have a few slides that gets into an overview of the Helius PFA software. And this may sound similar to either scripting methods or the Moldflow structural analysis or structural alliance tools that you've used in the past to transfer Moldflow results to your finite element analysis packages. And so I'll do my best to really compare and contrast really what the additional flexibility and features are when using Helius PFA. First on this slide, I want to cover that Helius PFA really was developed to provide more flexibility when taking Moldflow results and applying them to your finite element analysis model. And so we support really dissimilar models in that you can have different geometric features. Perhaps there's additional processing that we do to our injection molded part before we run it through our structural analysis, like as in adding holes or trimming certain portions. And so those geometries don't have to match up one-to-one to be able to transfer properties across. We can also have different meshes. Now this differs from the scripting method, which required the mesh to be the same in Moldflow and the finite element analysis package. And this gives us the flexibility to design the Moldflow mesh to be tailored for the CFD or the Moldflow analysis, and then have a structural mesh that's intended for structural analysis. Oftentimes we'll see, we require multiple elements through the thickness for three-dimensional analysis in Moldflow, and perhaps on the structural side we can get away with fewer elements through the thickness. So whereas we might have 20 or so elements through the thickness on our Moldflow model mesh, we can get away with maybe 4 or 5 elements through the thickness on our structural analysis mesh, which gives us a more efficient analysis. We also support different positions. Now this is one of the main feedback items we got when using scripting or the Moldflow structural alliance tool, is that the coordinate system for the FEA model and the Moldflow model had to be the same. Now as you see on the screen, we can define and create our models in completely different coordinate systems, and there's tools within the Helius PFA software that allow us to either automatically or manually align these two models. And it's just a temporary alignment. It's not changing nodal coordinate locations or anything like that. It's just a temporary alignment so that we can accurately transfer properties across. And then the original FEA input file is not modified. So we still have the same coordinate systems, the same nodal coordinate systems. In addition to supporting different types of geometry and mesh, we can also map to assemblies. And that's what you see on the screen here. And so this was a big leap forward for this workflow, because now when we're doing our Moldflow analysis, we're typically injection molding single parts, but those single parts then become as part of an assembly that we want to run our structural analysis on. So what the workflow allows for now is we can have multiple Moldflow studies on different parts, and we can map the information from each individual Moldflow study to an individual part within our finite element analysis. And this gives us the flexibility to run the as-manufactured analysis on the full assembly of our finite element model. The mapping process supports 3D to 3D, so solid to solid mapping. That means 3D meshing within Moldflow can be mapped to 3D meshes within your finite element analysis package. And then shell to shell, or 2D to 2D. This means that we can use a midplane mesh within Moldflow to map the results to a 2D shell mesh in our FEA analysis. The one mesh type that we're missing in this workflow is dual domain. So we have to go from 3D to 3D or shell to shell. There is no workflow for mapping a dual domain mesh to a 3-dimensional or 2-dimensional structural analysis mesh. Now let's take a look at the types of map data that we can utilize Helius PFA to transfer from Moldflow over to our FEA package. As I mentioned in the introduction, we can transfer nonlinear material properties. This means that not only are we transferring the stiffness and Poisson ratio of the plastic material, but if we do have nonlinear stress strain data for our particular plastic material, we can enter this data within the Helius PFA software so that we can represent the fully nonlinear mechanical response of our plastic parts. We also can transfer fiber orientations. This is very important, as you'll see on future slides, for fiber reinforced plastics, because as soon as we add glass or carbon fiber fillers into our plastic material, we turn a rather isotropic plastic material into a much more anisotropic composite material. And you'll see an example of that on the future slides. We can also utilize this mapping process to map across residual strains, and this will allow us to do a warpage analysis within our FEA structural package. The warpage analysis will be very similar to the warpage analysis we can already do within Moldflow Insight, but it just gives us the additional flexibility to tailor our structural mesh and boundary conditions on our structural part so that we can get the boundary conditions on our structural part and we can see how the part will warp when it's constrained as part of an assembly or part of a fixed constraint environment. And finally, one of the newest features is we can map across 3-dimensional weld lines. Now, this is very important for both fiber-filled and unfilled plastic materials because, as we know as plastics engineers, those knit lines, weld lines, those are where our parts are structurally the weakest because we have a boundary where polymers are not crossing the boundary or fibers are not crossing the boundary. So we have a weakened area, and we can account for that weakened area by transferring across 3-dimensional weld lines. And you'll see a few examples of this in upcoming slides. Now, as I talked about, when we have fiber-filled plastics, why do fiber orientations become so important? So here's just a simple stiffness example where we have a section of a part where the fibers are predominantly aligned in the X direction, up and down on our screen, versus when the fibers are a little bit more randomly aligned. And so we have 2-dimensional random alignment in our section. And we can see just by looking at the stiffness, the Young's modulus in this case, that we have, when the fibers are aligned, when we look at the stiffness in the X and the Y direction, we have a very orthotropic or anisotropic response. The stiffness is almost 3 times higher in the X direction than the Y direction. When we have random alignment, our material reverts back to a more isotropic stress state or stiffness state where we have stiffnesses that are equal in the X and Y direction. And then, of course, we have almost an infinite spectrum of possibilities in between when we have fiber-aligned alignment and random alignment. So you can imagine there's a continuous spectrum where these stiffnesses vary depending on the alignment of the fiber and which direction we're loading relative to the fiber orientations. Now, this becomes very important to use in our structural analysis because if we assume isotropic material properties, we can be either over or under predicting the stiffness of our part because we're not accounting for the influence of the fiber orientations. That was just a stiffness example, but also if we look at the nonlinear stress-strain response, not only is the stiffness differences evident in this plot, But we can also see when we have a fiber-aligned section of our plastic part and we're applying a load in either the 0, 45, or 90-degree directions, we have very different nonlinear plasticity behavior. And we also have very different levels of stress at which those particular areas will fail. So you can see the last data point on each of these three blue curves is the rupture stress of our plastic material. And it varies almost, in this, for this particular material, we can see maybe a 60 or 70% increase in the strength of the material when the part is loaded in the orientation of the fibers versus 90 degrees to the fiber orientation. So not only are the stiffnesses, which affect our deflections, going to be important to account for, but also if we're doing a stress analysis to start to hone in on areas of our part where we have high stresses, where we suspect our part may fail and rupture, it becomes very important to make sure that we're using the correct rupture stress in order to make that comparison. Now let's take a look at weld surfaces. So this video is showing a filling pattern where we're getting three sets of outputs in Moldflow. You can see the filling pattern in the upper left-hand corner. Let's first focus on the bottom left-hand corner, and this is the surface weld line formation plot that we can view within Moldflow. These are where we'd expect to see weld lines forming on the surface of our part. But this is just surface formation. This doesn't tell the complete story of how these weld lines extend three-dimensionally through our part. To get that three-dimensional representation of our weld surfaces, we refer to the two plots on the right-hand side. Now, the way these two plots differ is Moldflow has the ability to calculate where these three-dimensional weld surfaces form, but perhaps more importantly for our structural analysis, we can also track how these weld surfaces break apart and move as we continue to fill and pack out our part. So this is a very important distinction to understand because the final weld surface location is what we're most interested in from the structural analysis. Not the formation location, but where those weld surfaces fragment and end up in our part, because that's going to be where our part is structurally the weakest. Not at where the weld surfaces form, but at where those weld surfaces eventually end up after the filling and packing process. Now, I have an example that shows this a little bit more, where we see quite a bit of difference between the formation and the final weld surface location. So in this example, we have a pedal part that is injection molded, and we see on the left-hand side is the location of where these three-dimensional weld surfaces form. But as we're filling and packing out our pedal part, we can see these weld surfaces go from a little bit more discrete areas. These weld surfaces start to fragment and disperse through our part as we continue to fill and pack out our part. And it's the weld surface location on the right-hand side that's most interest to structural analysis engineers, because again, it's those places where our part is going to be the weakest. And so accounting for the stress concentrations and the difference in material properties that occur there, that gives us more accuracy in our stress analysis for our structural analysis. Now, why do we necessarily care about weld surface formation? Again, there's the aesthetic aspect. There's the surface weld line formation that can result in some nasty visual defects on the surface of our part. But for the purpose of this presentation, I think it's important to focus on how much the structural performance of our part can vary. So in the picture on the right-hand side, you see an example of a fiber-filled material where we have an area on the core, on the inside of our thickness, where the fibers are able to bridge where the two flow fronts come together. And that's where we're going to have a rich bonding area, and we're going to have more structural integrity at the core. But what happens on the inside and outside, in the shell portion of our three-dimensional part is the fibers aren't able to bridge that gap. So you can see they kind of flow down in towards the core, and what happens is even is just through the thickness of even though this is a butt weld, two flow fronts are coming from left and right, we can get a three-dimensional variation in the structural integrity of our part because of where the fibers are able to bridge the weld surface and where the fibers aren't able to bridge, and so we have more of a neat resin material behavior. Now, one of the common approaches for how to account for weld surface, the reduction in strength at a weld surface location, is to have a knockdown factor. And this data table is actually from 1976, and so it provides an overview for different types of crystalline and amorphous plastic materials with different levels of glass fiber or carbon fiber reinforcement. If you focus on the very right-hand column, the N percentage, this can be thought of as how much the strength of that plastic material at that location is reduced. So let's just take a look at a few of these. Let's first notice these types of plastic materials that don't have any reinforcement. We see at weld lines, the knockdown factor isn't that bad. If we focus on the top row for our polycarbonate amorphous resin, we see that without any reinforcement, the knockdown factors or the factor to apply to the strength of the material is 99, so 99%. So we have 99% of the strength of the material at that weld surface location. That's pretty good. But now let's focus on that polycarbonate. Now, as we add glass fiber filler, as we move down to especially the 30 and 40% filled materials, let's start to look at those knockdown factors. We're starting to get materials that only have 65% or 55% of the strength of the pristine, neat material. And we can see as we look through these tables, those aren't the most extremes. Let's look down at the very right-hand corner where we have a glass fiber filled PPS material. That material only has 20%, 1/5 of the strength of the neat material versus at a weld surface. So this is why it becomes so important to account for weld surfaces when we're doing our stress analysis or strength analysis, because of these factors that we need to apply that reduce the strength of our material at those points. Now let's take a look at a practical example of how this would be applied in a simulation environment. On the right-hand side, you see a dog bone specimen that's been injection molded in two different ways. In the top picture, there was a single gate on the right-hand side, and so we have a uniform flow through the dog bone specimen and no weld lines are forming. In the bottom picture, what you see if you look very closely is you have a double gate. You have a gate on the left-hand side and you have a gate on the right-hand side, and they're injection molded at the same time. So what happens is those flow fronts come right together right in the middle of that dog bone specimen, forming a nasty butt weld right in the middle of that coupon. What we did at Autodesk is we went and pulled these two coupons in tension. And you can see the location, again, focusing on just the pictures, not necessarily the simulation yet, but you can see in the pictures they fail in different locations. The bottom picture, where we see the butt weld right in the middle of our coupon, fails right in the middle, right as we expect. And then there's a different failure location when we don't account for the weld surface, or when there's no weld surface, you can see it fails up near the necking region where it necks down from a thicker thickness down to a thinner gauge section. And what we did is we measured the stress level at which those two coupons failed. So now focusing on the left-hand graph, you see two dotted lines. You see a black dotted line and a pink dotted line. Those were the experimental levels at which these dog bone coupons failed. So you can see right off the bat, before we even apply any simulation, that if we have weld lines forming in our part, we can have a reduction in strength of our parts, in this case the coupon, by almost 1/3. We see a pristine coupon that doesn't have a weld surface with a failure stress of, it looks like about 83 megapascals. And that drops way down to 31 megapascals when there is the presence of a butt weld. Now let's look at how the simulation, when we account for the weld surfaces using Helius PFA, how those will match up with these experimental results. What we did is we went and created a finite element model and a mold flow model of these coupons, and we, in the top picture, very similar to the real world example, we filled this dog bone coupon from right to left and did not have a weld surface located in our coupon. And in the bottom picture, we filled it again from both sides, so we got that nasty butt weld right in the middle of our coupon. And when we ran the simulation and actually allowed the simulation to predict rupture when a part would break, exceed its stress level and break, exceed the strength level for that part and break, what we see is the failure locations match up very good between our experiment and simulation. We're capturing where the rupture occurs in the simulation without the weld surface, but we're also capturing, when accounting for where that weld surface forms, we're moving and shifting that failure location to the appropriate location at which the coupon fails. So we got the failure location down through simulation by accounting for the weld surfaces. Now let's look at how well the simulation was able to account for the strength of the material when we're accounting for the weld surfaces. First, let's focus on the blue curve. This was when there's no weld surface, and we see the nonlinear response, and we see the simulation comes in just a tad high, but that's great correlation because we had good nonlinear material properties in order to predict this relatively simple stress state, right? So we'd expect these simulation results to be quite close. But what's really important to focus on is that when we applied the knockdown factor for this particular material, we got the green curve. And so just by applying the knockdown factor for this butt weld, we were able to, again, very closely predict the simulation, the resultant strength of the material when we compare it against the experiment. So the important takeaway here is that by having quality nonlinear material properties and by applying the appropriate knockdown factor for that material, we can get great correlation both for when there's no weld surfaces and when there is weld surfaces in our part for predicting rupture in our plastic parts. Now let's shift over to the idea of how plastic materials behave in tension and compression. And so on the screen here, this is a fiber-filled material. So you see the 0-degree response on the left-hand side and the 90-degree response on the right-hand side. And you see two groups of curves. You see a group of black curves that represent 4 coupons tested that represent the compressive response. So this is just the absolute value, so there's no negative stress in this case, so that the tension and compression responses could be plotted on the same plot. And then the dashed curves in both cases represent the tensile response. Now this is vital because look at the difference in the stress-strain behavior between when we're pulling our plastic in tension versus placing it in compression. What we see is the initial stiffness is the same. You know, that's what we expect. We expect that initial stiffness to be the same in the tension or compression. But what happens is we see two things happen. We see with the tensile behavior, we see plasticity occurs and evolves much more rapidly. Those curves start to bend over much more rapidly than they do in compression. The second aspect is we see that the failure stress is much lower in tension than it is compression, almost half in this case. And one final aspect I'd like to point out is let's think about how when these plastics do rupture, how they break. You can imagine in tension that once we start to get rupture, the parts separate into two pieces. We have this immediate drop off to near zero. That's where these downward vertical lines show up on the tensile coupon behavior. But in the compressive behavior, it's a little bit different. We get the peak stress and we get a drop, but it doesn't drop to zero. Because when we fail in compression, the failure mechanism is different. And even though the plastic material is failing in compression, we're still able to hit a load plateau, and we can extend out to a very high strain level, 9% in the 0-degree direction, and looks like about between 7 and 9% in the 90-degree direction. So there's three important things to take away here that differ between the tensile and compressive behavior of plastic materials. Plasticity evolves much quicker in tension. In tension, our failure stress will be at a lower point. And also the failure mechanism will be different for tension and compression. Compression, we get that load plateau. Tension, we get rupture and drop off to zero. So what this tells us as structural analysis, as plastics engineers, is that if we want to be able to not only predict the correct deflection, so the stiffness response of our parts, but also predict the correct strength of our parts, we need to be able to differentiate between tension and compression. And that's what we're able to do within Helius PFA. So again, previous methods within Autodesk Moldflow for transferring properties, we were able to transfer linear elastic properties and tension. Now we've expanded that to include nonlinear properties in tension and nonlinear properties in compression. So what you see on the screen here is a plot of the raw data for tension and compression in the 0, 45, and 90-degree directions, and then how the material model behind the scenes that's developed to represent that test data, how that overlays on top of our experimental data. And this gives you a little bit of insight into how the material inputs for using Helius PFA work. And so what's required if we want to do a fully nonlinear analysis is we do require experimental stress strain data in the 0 and 90-degree direction. Now what I mean by that is, let's imagine we're injection molding a plate. And so we have like a fan gate, and we fill so that all the fibers are pointing in one particular direction. Now we want to cut out two coupons from that plaque. One coupon that represents the flow direction, and one coupon that's 90 degrees or orthogonal to that flow direction. It's those two directions that are going to be the basis, the minimum input required in order to perform a nonlinear analysis using Helius PFA. Now, you heard me earlier mention about the 45-degree curve. This is where we have that same plaque, and just to fully define and characterize our material, we can also add the 45-degree material response in tension and compression. This will give us the most accurate representation of the material, but if all we have is 0 and 90 degrees, we see this a lot from material suppliers and test labs where they test at 0 and 90, but the 45 data might not be tested for. And so what the Helius PFA software requires is the 0 and 90, and it will assume a 45-degree behavior if not supplied. But the best practice is, if the 45-degree test data is available, let's go ahead and use it. Now the other distinction here becomes, well, what happens if I just have tensile data? Maybe I haven't gone and done the compression test. And that's okay, because what the Helius PFA software will do is, if all you have is tensile data, it'll just flip those tensile curves around into the opposite quadrant and utilize the tensile behavior as the compressive behavior. Now, as we saw in those curves earlier, that might not be the best way to approach it, but it's all about, how accurate can we get our simulation with the data that we have available. And so the idea here is we wanted to provide the flexibility to get the most accurate structural analysis of our plastic parts as possible, but if we don't have the full gamut of data in tension and compression, we can get by with those assumptions, but just keep in the back of your mind that those assumptions aren't going to give us the most accurate structural analysis. And the final point I wanted to conclude with before I wrap up this presentation is that I've been talking about how the input data is at 0, 90, and optionally 45. But what happens when the fibers aren't aligned? And what happens if there is loading at 30 degrees relative to a coupon, or the fibers are more randomly oriented? How do we represent the material behavior there? And this is one of the unique aspects of the software, that it's called multiscale material modeling. And what this means is we have two pieces of information. We have fiber orientations that we get from our Moldflow simulation, and we have a plastic material model. Now, this plastic material model that holds these fibers, this material model is what is determined based on the input data. Okay, so let's think about that again. The input data is the stress strain curves for a nonlinear analysis in the 0 and 90-degree direction, and optionally 45. What the software will automatically do is come up with a Ramberg-Osgood plasticity model to represent how the actual plastic that's holding these fibers, how that plastic would behave. Okay, so this is the idea where multiscale comes in. We have a composite material that's plastic and fibers, but the software will automatically back out how just the plastic would behave. We know the fibers, we know the stiffness of the fibers, we know the orientation of the fibers, so the software can back out how the actual plastic would behave. This is the idea of multiscale. Now, this is important because once we have that plastic material model, it's the same everywhere in our part. What changes is the fiber orientations. Okay, so the fiber orientations change, and when we look at our part, we're going to have different stress states, right? We're going to have areas of our part that might have a stress in a particular direction, and we shift to a different place in our part, and we might have a different stress state. So this allows us the flexibility to account for point-by-point variation in our material behavior based on the fiber orientations and how our part is being loaded relative to those fiber orientations. Now, this is super valuable because we get an accurate representation at each point in our injection molded part. We get a separate set of stiffnesses and strengths based on those fiber orientations and how they vary through our part. And that's where I'd like to conclude today's presentation. And again, just to recap really quickly, Helius PFA is a tool that was built upon the foundation that we initially developed in Moldflow for transferring Moldflow results to our structural analysis. This included scripting and the Moldflow Structural Alliance. But the main differentiator that we see with the Helius PFA software is we expanded on the capabilities. Right? We saw that there's flexibility for how we handle different mesh types, assemblies, different orientations for where our models are created. And we've also expanded on the accuracy of the material model. We can now account for nonlinear material properties. We can differentiate between tension and compression, and we can account for weld surfaces. So Helius PFA was just building on previous efforts within Autodesk to provide these tools that allow us to transfer results from Moldflow to the structural analysis. And this is our culmination to provide a tool that allows us to complete a workflow so that we can utilize those Moldflow results to run an as-manufactured structural analysis. And that concludes what I wanted to talk about today. And so, Beth, I'll pass it back to you, and we can answer any questions that popped up.
Great. Thanks so much, Dan. So we do have a couple questions in here. We also have a couple others behind the scene. Kristen has joined us as well, and she's been answering questions along the way. So thanks so much for that, Kristen. There's a couple I thought we could kind of reiterate out loud. So Dan, if you wouldn't mind, in case we had a couple users who joined a few minutes late, can you just briefly go over again who was offered with their licensing, who's offered the Helius, and what version of the license and what year version of the product you need to have access to Helius PFA?
Absolutely, Beth. I'll switch back to the original slide that I shared. And so, again, just to reiterate here that any and all users, subscribers to the 2018 version of Moldflow Insight Ultimate will automatically receive an entitlement to the Helius PFA software. Okay, that entitlement's only provided at the Ultimate level, and it's only provided to subscribers. Okay, now there's a whole group of users that are on maintenance for Insight Ultimate, and there's also users that are at the premium and standard levels. Now the workflow is exactly the same between all these levels, but the Helius PFA software would have to be provided as a separate license for users on Insight Ultimate Maintenance, and then also on Premium and Standard.
Perfect. Thank you very much. So let's see. Another question we have here is, do you know when like Autodesk, Nastran, and CAD would be supported with Helius PFA?
Yeah, we do have to be a little bit careful about forward-looking statements. What I can share is that it is on the roadmap, and we expect this integration to occur in an upcoming release this year. That specific time frame we can't disclose, but we do expect it to be sometime within the 2018 product release cycle. In a minor release coming up, we do expect that integration to be complete at that point.
Great. Thank you. Okay, so we have a question in here. If you export residual stress from Moldflow and then you fix, and it looks like we have zero diff, some nodes and ANSYS, would you have convergence problems?
Yeah, I'm looking for this question real quick. I just
Sure.
want to read it too. Okay, I see it
Definitely.
down there at the bottom.
Yep.
If you export residual stress from Moldflow, and then you fix 0 degrees of freedoms in some nodes and ANSYS, don't you have convergence problems? Okay, there's a few questions in here I think that are very important to touch on.
Great.
Residual stresses are tricky to account for. And the reason is we know in plastic parts residual stresses exist. That's the nature of injection molding, that's the nature of plastics. We get differential shrinkage, we get out of plane and in plane shrinkage, which could contribute to warpage. So we know when our part comes out of the mold and cools down, there's residual stresses there. We know that. We can view plots of those residual stresses in Moldflow. Okay? The trick becomes when we're accounting for those residual stresses in the structural analysis, we have to be careful, right? We can't just map those residual stresses from a part analysis from Moldflow to our structural analysis because it can be misleading. And the reason for that is that we know that all plastic parts have residual stresses. So what that means is the coupons that we're using to generate our data, our material properties, have residual stresses. All right, so here comes the tricky part, right? We know there's residual stresses, but the test data that we're using to evaluate how bad or how harsh those residual stresses are compared to test data where those residual stresses aren't accounted for, right? They're zeroed out. We look at that stress strain curve, that first data point's at 0, right? And so this is where it becomes tricky and it becomes misleading because, okay, we run a Moldflow analysis, we see there's residual stresses. Oh, shoot, they look kind of high. They're past maybe the yield point of my material. Well, yeah, they're past the yield point of your material that was tested on a coupon that did not account for residual stresses. All right, so that's where the tricky part comes in. And so the approach we took is, hey, 99% of the data out there is going to have is going to be representative of 0, of not accounting for the residual stress, right? That initial stress state's 0. Okay, so either we have to account for residual stresses in both our test data and our part analysis, or we zero it out in both places. And since 99% of the data sets out there, the test data is zeroed out, well then, unfortunately, we're going to have to zero it out in our part. So I can kind of see where this is going, right? We know there's residual stresses, but we have to zero them out. Is that going to give us an inaccurate analysis? And so what turns out is that as long as we're zeroing them out, because the residual stresses are not accounted for in our coupon data, our test data, we have to zero them out in our part data. As long as we're doing that, we're okay. We can still get great correlation between our simulation and experiment when we zero those out. But in order to get that correlation, we have to account for what I call the big 3, right? We have to account for fiber orientations, we have to account for weld surfaces, and we have to account for nonlinear material properties. If we're accounting for those 3, we can get exceptional correlation between simulation and experiment when we zero out those residual stresses. Oftentimes what I see is we'll look at plots in Moldflow and go, oh my goodness, the residual stresses are so high. This is why my structural analysis might not be matching up with what I'm seeing in the real world. And that's slightly true, right? There's residual stresses there. You know, it would be best to be able to account for them, but we can't account for them if we're not accounting for them in our test data, right? So as long as we're accounting for the big three, fiber orientations, weld surfaces, nonlinear material properties, and zeroing out those residual stresses, we can still get great correlation between experiment and simulation. Okay, so that was kind of half the question there. The other half was, you know, what happens when I fix my degrees of freedom in my structural model, and then transfer the residual strains across to allow warpage to occur? Will this cause convergence problems? And convergence problems are part of a larger discussion that maybe I won't go into as part of this answer. But in terms of just being able to simulate warpage with degrees of freedom, we won't encounter convergence problems there, because that's one of the unique aspects of using Helius PFA to run our warpage simulation, is we can create our ANSYS or our FEA model and apply the boundary conditions, or have that part as part of an assembly, map across residual strains so that we can simulate the warpage of the part. And that way we can look at the warpage of the part as it would be assembled as part of an assembly or constrained within a constrained environment. So we won't get convergence problems because we're just applying an initial residual strain that allows the part to deform and warp, but it's constrained by the ANSYS model, so that we can actually replicate how the real world warpage or deflection or deformation would look when it's in that constrained environment. Okay, I think I went in pretty deep on that question. So
No, great. Thank you.
I hope that answers. Yeah, we'll go ahead and move on.
Sure, and it looks like there may be a quick follow-up to that one listed as the last question there. So related to the last answer, do residual stresses move to zero over time?
They move to, they don't move to zero. They move to, okay, so let's go through a little thought experiment here. We injection mold our part and it's constrained by our mold. At that point, there's no deformation, so there's no residual strain. But because your part's constrained by the mold, there's internal residual stresses. So what happens is we remove the mold, we pull our part out, and what happens is that part warps, right? It shrinks, it warps. So that relaxes some of those internal residual stresses, but they don't go to zero. They go to a lower value, but they don't go all the way to zero. So any plastic part sitting out there is going to have some sort of initial or residual stress in there. It's just the nature of plastic injection molding processes. Those residual stresses do decrease, and we can go through additional processing conditions like annealing to even decrease those residual stresses even more, but they won't go all the way to zero. We can never get them to go all the way to zero. It's just the nature of differential shrinkage and cooling and core versus shell behavior. There's too many aspects going on at once with the injection molding process to get those residual stresses to truly go all the way to zero.
Great, thanks, Dan. Okay, one other question here. Is Helius able to do an analysis on a two-shot part, and will it account for the material remelt area if it does?
Yeah, let me think about this one for 1 second.
Sure, yeah, absolutely.
Now, Beth, I don't have as much experience in Moldflow as I know you do, and,
Sure.
and a few others on the call. Can you briefly explain what's meant by two-shot?
So most likely an overmolding analysis.
Okay.
Where there would be two components, so two different plastic components.
Understood. Okay. In that case, I suspect the answer is no. I can verify that to make sure, but I suspect it's just a single shot or a single injection molding process. So overmolding, where we injection mold a particular material and then overmold it with a secondary material, and there's some remelting at the interface, and there's some mingling of the different polymers. I don't think the software accounts for that at this point, but I'll double check that.
Sure, and maybe as an alternative too, if there are two components and you are interested in this information, you could run each individually and evaluate them that way. That wouldn't account for the remelt area, but it would account for each component individually.
Yeah, I think that's a great point to bring up, Beth. Account for two different parts, and then you can just treat those as an assembly within your FEA model. But yeah, the remelt region wouldn't have the effects of remelt.
And from there, it looks like we've touched on most of these questions in here. And I know, Dan, you and I were talking offline beforehand. If any more questions do come up, we would definitely encourage you. There's kind of a couple places you can post them right now. So you can either kind of post to the Moldflow Insight forum, or there is a separate forum for Helius PFA. Is that correct?
Yes, that is correct, Beth. So for those of you that are familiar with using the Moldflow Insight question and answer form for posting questions, there also is an equivalent form for Helius PFA. And so if you're accessing these forums either through the SimHub website or through other web pages on Autodesk.com, the Helius PFA form will be in the exact same location as the Moldflow Insight form. So any follow-up questions, they can be posted in either form, and an answer, those questions will be answered. And then what I've seen a few questions that come in about, okay, this is interesting. I want to learn more. So what I encourage you to do is reach out to your Autodesk technical specialist for Moldflow or the sales team that you're working with at Autodesk, and we'll be able to coordinate a more in-depth demo or talk more about your specific processes, your materials, if you want to continue this conversation to learn more how it apply for your unique individual challenges.
Perfect. All right. And with that, I think that concludes everything. Thank you very much, Dan, for joining us today and for giving this great presentation. And I think we'll leave it at that. So have a great rest of your day, everyone. And thanks again, Dan.
All right. Thank you, everyone.
Thank you.